In your class, you already have, or you will soon be learning, about how to combine radical expressions such as these. The square root of 6 times the square root of 8. We not only want to combine them, but we also want to give them in lowest form, simplest form, we should say. So one way that we can do this is to just combine them into one radical expression, evaluate that, get the square root of 48, and then simplify it. Square root of 48, well, that's equal to the square root of 16 times 3. And so that's equal to the square root of 16 times the square root of 3. And so that's equal to 4 radical 3. That's our final answer there. But what if we wanted to combine expressions like this? The first step is going to be the same. We're going to be multiplying them together. So we'll multiply these two expressions together. I'll get x to the 7, because x to the 2 times x to the 5 is x to the 7. Not x to the 10. Remember that. When we are multiplying the exponentials together, we add the exponents. When we multiply the monomials, we add the exponents. So y to the 1 times y to the 3 is y to the 4. But now what? When we have numbers, we know what we can do. We can look for perfect squares and then take them out. Well, with variables, it's that same strategy. We're going to be looking for perfect squares and we take them out. But they're a little bit trickier to see. Perfect squares as numbers, you know what they are. 1, 4, 16, 9 is the previous one, and then 25, and 36, and 49, and you know the rest. So it's important to remember that the reason why x squared, well, we'll say it this way. The reason why the square root of 25 is equal to 5 is because 5 squared equals 25. In other words, the square root of x squared is equal to x because x squared is equal to x squared. What this means is that when we have something like x to the 6, well, now we need to think about what exactly that means. So as another example, consider this. So I want to know, what is the square root of x to the 6 equal to? So consider this, square root of 64. Well, you should know that that's 8. But 64 is a power of 2. If you multiply 2 by itself a bunch of times, you'll eventually get to 64. In fact, it's exactly equal to 2 to the 6. So when I say the square root of 64, what I'm kind of saying is the same thing as saying the square root of 2 to the power 6. And as we just said, the square root of 64 is equal to 8. Well, 8 is 2 to the 3. So we're saying that the square root of 2 to the 6 equals 2 to the 3rd. So what happens to that exponent? It gets cut in half. So when we say the square root of x to the 6, what we're saying is, well, that's equal to x to the 3rd. Another example to maybe make this a little bit clearer to see. If I have the square root of x to the 10, well, that's the square root of x squared times x squared times x squared times x squared times x squared. Since after all 10 is equal to 5 times 2, I can write out 5 expressions with 2's in them. By the reverse of this property up here, these are all now individual square roots. So square root of x squared times square root of x squared times square root of x squared, square root of x squared, square root of x squared. This gives me, of course, x times x times x times x times x, or x to the 5. So what you're seeing is that when we square root an expression with an even power, we're just dividing that power in half. And that's actually a really convenient way to think about things. Think of the square root as a power to the power of 1/2, a power of 1/2. So when we say this, think of it as this, x to the 10 to the 1/2. We're taking that x to the power of 10 and raising it to the further power of 1/2. And you remember your power properties, that when we have a power inside a power, we just multiply them. So half of 10 is 5. So think of a square root as a power of 1/2. So what that means, when I get to this point, I have the square root of x to the 7 times y to the 4. Well, I can break this back apart and say that's the square root of x to the 7 times the square root of y to the 4. And that we just said is going to be equal to y squared, because I take my exponent and divide it by 2. But what if we have an odd exponent? Well, it kind of works the same way, because this x to the 7 can be rewritten as x squared times x squared times x squared times x. 2, 4, 6, 7. And so this then is the same as just saying x to the 6th times x, which would be x to the 6th square root of x to the 6th times the square root of x. And so x to the 3rd times root x. In other words, we get the even power and we divide it in half. And we have that 1 left over. Because it's an odd number, it's an even number plus 1. We leave that 1 left out, or left inside of the radical. So putting this together, this is the way that I would recommend you approach these types of problems. Combine first. This is an important point. Combine first. So we did that. Then separate even exponents. Separate out even exponents. What I mean by that is I'm going to take this and rewrite it as x to the 6, y to the 4 times x. If that was a y to the 3rd or a y to the 5th, for example, then I'd have a y under there as well, but it's not. So we'll go with this. And then so my final answer is going to be x to the 3rd times y to the 2nd times the square root of x. That's my final answer of that thing up there. So combine the expressions first, then separate out the even exponents. I'll do one more example here. Let's see. The square root radical 12x cubed y over 14 radical 14xy. When we're dividing, remember that we put them together into one expression. Again, we combine. Just like we multiply underneath the radical in those cases, we're going to divide underneath the radical here. So I get 12x cubed y over 14xy. And now I can reduce. Let's see. Get some colored chalk. The y's cancel. The x to the 3rd will reduce with the x and just have a 2 left over. I'm going to write that. And then 12 over 14, I can take a 2 out of both of those. I have 6 and 7. So that gives me the square root, big square root, of 6x squared over 7. Now, I can't reduce that anymore, so now I go back to looking at the radicals individually. Radical 6x squared over radical 7. And then finally, that x squared, I can take that out. There's no perfect square that goes into 6, though. So that's going to be radical x squared times radical 6 over radical 7. And so my final answer is x radical 6 over radical 7. Now, as it happens, that's not technically the final answer. We need to do something called rationalizing. Essentially, we don't want to have that square root left over on the bottom. Anytime you have a fraction where there's a radical left in the bottom, we want to get rid of it. Check the next video, video 2, for an explanation of how that works.